Welcome to the P99 conference, the third one we have, and welcome to my keynote. I'm Laor, I'm co-founder and CEO of ScyllaDB, and I'll be speaking about quantifying the performance of sharded core architecture. We've been playing with that for quite some time. So welcome, enjoy my keynote, and enjoy the rest of the conference. We're really excited to have you around. And remember, this is a hybrid virtual and also a online conference, so you can interact with the speakers. A bit about myself. I've done a really cool project. I've been fortunate to participate in projects like KVM and OSV and Scylla. And when we did OSV, there is perspective on P99, so less is more, obviously. And when we did the OSV project, we used to give away swag of underwear with the word less is more. So maybe we'll repeat it in the next P99 conference. Outside of tech, I like to ride bicycles and also turns to visit orthopedic doctors. There is a cause and effect between the two. And beside that, I fight for democratization, sometimes of open source and sometimes of judicial system like we have in Israel. Now let's get to the topic. So let's start. The talk is about things and milestones that me and the team observed over the years, and lots of learning that we can share how we got to the thing. So it's not just here's sharded core. It's a fantastic architecture, but you can see through the milestones and projects that we were involved in, how we got to this concept. So initially, I started my career as working for a terabit router company, and I built a router and forwarding information base. This is a complicated data structure with lots of locking. But back in the days, we were using just a single CPU machine, and basically the locking is there not for performance, but for the threads are for software construct and not for performance and not for parallelism. Later on, I did some device driver code and kernel load balancing, so things began to be more low level. And I joined a startup called Kubernetes, where I met Avi Kividi. And initially we did a network device, but we had to pivot. So Avi came up with the idea of fault tolerance virtualization using lockstep. So we had main VM and shadow VM that tried to follow it to provide fault tolerance. And the idea was to clone all of the inputs, and the shadow VM is supposed to generate the same outputs if all of the inputs will be duplicated. Inputs like network packets, like block requests, and also interrupts within the same instruction boundary. And it really worked magically on a single vCPU. The year was 2006. So it's still the 2000s, and you'd expect everything would be SMP, but back in the days, we're contemplating whether it's a good idea for it to go out with a virtual CPU while SMP began to be a thing. And basically, this is what failed the project, because all of those CPUs synchronize through the memory, and it's too expensive to halt the memory sharing. So this failed, and luckily Avi came up with the KVM design, and I managed the team and also was an engineer and dealt with things like Virt.io. Started to do things like prevention of cache line false sharing, power virtualization, and other more sophisticated items. And after KVM, we opened this company. Initially, we did operating system, and we tried to build an operating system and specialize for virtualization and to load the apps into the kernel space to prevent user to kernel context switches. And we also implemented Van Jacobson network stack, and we'll cover it later. And after this idea semi-failed. Technically, it's still there. It's an open source project, active, but we failed to compete with Linux. So eventually, we pivoted into the database space and adopted Sharper Core. So that's kind of why we're speaking, and we'll cover all of these, and we'll double click pretty much everything. Uh, so let's start. So everybody knows locking is evil. Um, but we'll go through it anyway and realize how evil it is. Um, at the end of the day, if you like to lock something and to increment a counter, you have to have an atomic lock in the hardware level, in its instruction native code level, and you gain that in x86 by adding the lock prefix. In the early days, the chip would bus lock, and then nothing can be executed in parallel, and it's guaranteed to have an atomic semantic. Great, but horrible for performance. So Intel came up with an improvement in the P6 family and above, which is all of the modern processors, where you don't really need to lock the entire bus. It's okay, and the semantics of the lock, if we'll just prevent the cache line from being used by all CPUs and only by a single CPU, then we'll be able to translate it from bus locking to cache hierarchy synchronization. And that's what we have today. So great, this is the Bible in terms of if you are a low-level programmer, you use this Intel SDM manual as a Bible. Now, it didn't quite solve everything, but pretty much all of it. There's an issue if you make accesses that are not cache line aligned. If you do that, then the processor will automatically lock the bus, and performance will grow. So today there are detection mechanisms in the kernel that detects that. It's called split locking, and it's important because performance will grow. And this is an example of how to test it and to verify that suddenly you get 200x slower performance. It's also important in virtualization because you wouldn't want the guest to slow down all of the other guests. So that's important as well. Now, if we talk about virtualization and more challenges of locking, there's things like ticket locking. Ticket locking is not related to virtualization per se because it's there in order to provide fairness. If multiple processors compete to gain the same lock, then the one that runs within the CPU die and with closer to the actual thread will get the lock. So ticket lock is a more friendly way, and it also needs to power virtualize. There's even more things with power virtualization, like you wouldn't want to preempt the lock holder because then all of the other processor will spin for nothing. That's why we have power virtualized ticket locks. Now, I remember this from 2012 when this is the last year that I've been involved in the KVM project. But 10 years afterwards, not recently, still people send patches and enhancement to it. So it's still an interesting problem and a complicated one. So blocking is definitely complicated, but it's not just locking. It also takes time to invalidate the cache. We have L1, L2, L3 caches, and it's complicated. It will take time and it will slow your application down. How much will it slow it down? It depends. Let's assume, and you use a spin lock when there are not a lot of contention. Otherwise, you'll be spinning too much, and you should use another lock. And if there is no contention, this is the speed you're going to gain the lock if you own the memory that represent the lock in your own local cache, and also 50 nanoseconds if it's in the remote processor cache. And contention can cause it to be very, very expensive. So locking is evil, but actually not only it's not enough. Round trip is actually evil too. Um, this is a diagram of a modern chip. Now, these cores need to be connected to each other. They don't send information over Wi-Fi, so they're connected through a chain of interconnect within the die and also outside between the chips. Um, this guy, Jason Raymond, writes really nice blog, and he measured the round trip measurement between one core to the other, and he mapped all of them. So he emits all of the overhead of message sending and receival. Only calculates the round trip between the processors, and use the common AWS machine, a C5 machine with two main chips, two NUMA nodes, and 92 virtual CPUs. And you can see here the speed of the time it takes to traverse between, let's say, processor number 50, hyperthread 50 to hyperthread 92. So you can see the color, and the color represents, I'm not sure if it's cycles or nanoseconds, but these two are relatively close together. And this is the heat map. So very complicated. You can see the diagonal line. That's the speed it takes for hyperthreads that are neighbors on the same CPU, on the same core, to interact. That's the fastest. And on the remote end, you can see a case where it takes 18 hops to get from one core to another core. And that's part of the other NUMA node. That's the same data where it's flattened on a two-dimensional graph. So you can observe the big changes between the same hyperthread next to you to another hyperthread running on another chip. Let's look at another chip. So this is Ice Lake, another AWS instance, happened to be 128 vCPU machines with two NUMA nodes, and this structure is relatively flatter. It's friendlier, so you can have two main colors plus this tiny bump for hyperthreads in the beginning, and then the time it takes to travel within the die, and also the time it takes to travel across the NUMA nodes. So these things also takes time and translate to latency. So if we take it all together, if you build a library like gmalloc, then there'll be cases that you'll run within the thread, within the same hyperthread, the T-caches of a thread local structure. Could be that you'll miss it and it still be outside of this, but you'll have to do some locking and to access data that resides within another core, but without contention. And could be that you'll have contention, and could be that you'll have to call nmalloc, and then it will be horribly expensive. So lots of complexity when you're trying to maximize performance, and it's hard to get to a low P99, and this variance translates to a higher P99 with basic things like NUMA, but you also have locking and TLB flashes and system calls and so forth. So let's proceed to a more higher level structures in the stack. So we came across Van Jacobson. Is one of the fathers of TCP/IP, and in 2006 he came up with a really interesting design to speed up networking in Linux. But it was a general concept called net channels. And basically, you can think about it as in order to, instead of solving a problem, you can just bypass it because geniuses prevent even hitting the problem. Do you know who said it? Well, it's not Van Jacobson and it's not Bob here. It's Einstein, actually. So Van Jacobson measured the Linux kernel, and he measured a uniprocessor and dual processor scenario, and he ran netperf. and it got certain performance with it. And you can see that the busy time of a single CPU was 50% of the time busy. With two CPUs, the system was 77% of the time busy. But the app on the right hand actually consumed only 1% of the processing. Everything else was TCP/IP. Well, that's not surprising with NetBirth, but that's still like the discrepancy is quite big. And this is because there are lots of models within the kernel that steal the time, and all of these models need to synchronize and also to notify each other. And this is a lot of locking and cache line bouncing messages. So he came up with a channelized implementation of the TCP/IP stack, and the idea was to move more to move code and processing from the interrupt level up to the app level. So in the orange, you can see where he moved some of the processing outside of the interrupt and soft RQ to the driver. It still didn't help much. It actually even slowed down things. Later on, he moved more processing to the socket layer, and there he got a big gain, so 28% utilization, much better. And eventually, he used the user space TCP/IP stack, and this is where the most gain was achieved, and only 14% of utilization got. I bet he saturated the link, and then you get the maximum efficiency and the minimum amount of balancing of data and messages between the components. So less components is better, obviously, and having the processing of the data be as close as possible to the usage of the data in the app makes the most sense. And so that was really remarkable achievement. And it's not common who uses user space TCP stack. Very rare. Some of the audience and some of the presenters do use it, but it's quite rare. And most of the case, it's not justified. So this pretty much gave birth to our shard per core implementation, because we hated locks. We knew from the KVM days that locking is evil, and even if it's not contended, it's costly. We were familiar with Van Jacobson design to move things more to user space. And we also saw examples of databases that require 300 machines in order to execute 1 million operations per second. And that's screamed from inefficiency. So we wanted to solve that. Now, even before we started, Avi already did several projects of storage, and they all had shard per core design. So it's not just we came from this, but it's really good for my story. So let's just continue. So shard per core, it's not the first time we presented, so I'll be super fast over it. The main talk was to give you all of the history, how we came here, and you can stop in adopt only partial implementation of the design and the architecture. And also there's also a future element where we add new tests to it, and we verify that the architecture really works. And that piece is new. So shards better than threads, which is a mess. And obviously, with traditional stack, you have lock contention and cache contention and NUMA unfriendly. And instead, if you shard everything like on the right hand and have every virtual CPU, every hyperthread run the same thing without much synchronization, and with locking and pinning of the RAM to that CPU, and also usage of the NIC, and you can virtualize the NIC so it will have its own queue, then everything will run in parallel. So that's what we do. And also, instead of having a CPU scheduler, and we use standard Linux kernel, but the problem is with many threads that they have each their own stack, and it can be expensive with thousands of threads. Instead, we have just basically, in theory, one thread per core. We actually have two, doesn't matter. And we use our own building blocks to schedule future and promises and continuation. That's what we have with Scylla. And lastly, we have this IO scheduler because IO is shared by all of the cores together. And there's not enough disks to have one disk per chip, per core. So we have an IO scheduler to make sure that no single shard can overtake the capacity of the other shards. And basically, we make sure that they divide and behave well together. And we've done several presentations only on this IO scheduler alone. So I won't get into it. Let's just see if it works in practice. Like a spoiler, it works. That's a screenshot from top of a I4I metal machine with 128 virtual CPUs, and you can see all of them work at 100% speed. Actually, some of them, and I'll make it easier for you, are not working at 100% because we decided that every 30 shards will have 2 shards that don't use data and they're reserved for interrupts. And they're also a per NUMA node as well, so that they don't get to 100% processing. This is another view of top and another magnification, so you can see the 2 shards that aren't assigned to data and they do just RAQ. That's why they have high software interrupts there. We do see also some regular shards that have high system time and also some software interrupts. And this is not good, and we plan to solve it in the future. It's not bad either, but it can add latency, and we're going to solve it, and I'll cover it. So Scylla is capable of running on small machines, on large machines. The question is, what machine would you take? We advise to take the largest possible, so to scale up before you scale out. You first fulfill your high availability needs and then select bigger machines until they're full. Why? Because if every machine, let's say, fails one day every 365 days, then if you have many machines, then you'll have many failures. Also, the ease of maintenance, if you need to do a rolling restart, then you have just fewer machines or an upgrade. You have no neighbors, many times no virtualization, no container overhead, less moving parts. So let's check this assumption, whether it's really possible to switch from many small machines to fewer large machines. So we take, for example, the AWS, but it can be any other cloud, I4I instance family. And you can start with a very small instance with 2 virtual CPUs, memory, storage, and network, and cheap cost. And you can double it, all of the units all the time. So every time you go down 1 row here, cost doubled, but you have more virtual CPU, double the memory, double the storage, double the network. I'd like to thank my colleague Felipe, who ran all of these tests and lots of tests to verify that we can run and scale through all of these machines. So let's start with the ingestion test. So what we've done is we loaded 1 billion partition to an extra large machine, extra large cluster. It's a machine with a replication of 3 machines of identical extra large, and we measured the time it took to ingest them at 100% CPU. So it was a bit over 4 hours. Then we repeated the same case with 2 extra large instances, which have twice the capacity and also twice the cost. So we also loaded twice the data, and we expect with fantastic scaling that everything will take the same amount of time. And actually it did. It took 10 minutes longer, but we'll ignore that for it's a relatively small um, variation. The same happened with 4x, 8x, 16x, and metal machine, which has 188 machines. So we scale perfectly with rising amount of cores and up to 32 billion partitions in a 3-node machine cluster. Really nice. It's also nice to observe. We did this experiment back in 2018, and it took us between 14 hours to 12 hours. So now it takes 1/3 of the time. A lot to this improvement. We have the i4 as a contributor, but also lots through it is software improvements that we've done. Nice things to observe. For example, if you check the Grafana monitoring, you can see that all of the threads are doing almost 18,000 requests per second per hyperthread. That's nice. And you can observe the latency, and the P99 latency is under 2 milliseconds when the CPU usage is almost 100% for shard. Also nice. Now the devil advocate may ask this question. So, okay, I'm convinced that you can scale when you ingest, but what happens if I have a failure? I need to replace a node, I need to add nodes or remove nodes in production, and will it take me more time to do that? So it's a fair question, and we tested it. And the quick answer is you're just as safe, because we tested how much time would it take to, let's say, replace a node. This is the light blue. And it takes only 30 minutes to replace the very big node. Also under heavy I/O traffic. It's not. To imitate a production use case. So we have some rise in the bigger machine for some reason. I think that we can repeat the test to check whether it's real or not, or just a one-time issue, but give or take, it takes pretty much the same amount of time. Also with the adding a node and removal of nodes, it takes pretty much similar amount of time. It's 1 hour or 2 hours. It's not a small amount of time, but if we're speaking about 10, 20 terabytes per node in the larger nodes, then that's a lot of work. And lastly, we also tested compaction. This is the process of combining many small files, small SS tables that the LSM tree generates, and combining them in a single file per shard. So we tested it without traffic. That's the bluish, and also the other blue color to do it while we serve traffic. And also everything is linear, so we scale just fine. I'm pretty excited with the result. I'm not sure about you, but if we drill down and see what we're doing is all of the shards perform at a pace of 70 megabytes per second in this accesses for compaction. So if you combine it, that's more than 8 gigabytes a second. That's quite a lot in an I4I metal machine. In the usage where we did it without additional read traffic, only compaction, the system managed to get to a record speed of 20 gigabytes, which is crazy. It's like I was familiar with 10, 12 gigabytes per second. Now it's a lot, and this is like it's a benchmark, but it's also a real use case, and we can get to that in production, and not in it's not an effort. It's a real use case. So the system performs just nice, and we do manage to scale up before you scale out, and shot per core really works nicely. So what's more, Avi has a really nice presentation about tablets because sometimes the data is not distributed nicely between the shards, and tablets solve that. So I invite you to Avi's talk. There's also challenges that when you have many connections to every shard, then we have lots of shards. Quick solve that because we move TCP out of the way, and you can have UDP. We have such a code, but it's not production scale, and we don't have immediate plan to do that. It's not a big pain, but it's an interesting direction. Another thing is the IO ring. We'd like to get rid of the interrupts. There is no need to run interrupts. We have dedicated cores that can process and to pull the network card. And also by doing it, we'll get rid of the software interrupts in the shards, and the shards wouldn't do any IO at all and wouldn't go to the kernel. They'll only go to the kernel once they know that the data is in the buffer. And lastly, you can take the shard per core concept and clone it, not just within the server, but also apply it into the client and have end-to-end shard per core design, which will perform really nicely. And also, it may help you to have assumption of how the data is distributed and the consistency of it. And some customer of ours are actually implementing this. So this is it. This is my super quick cover of shard per core architecture and implementation. You're welcome to connect through the conference, and also later on, enjoy the rest of the show. Thank you.